Today, we're so pleased to welcome Dr. Frank Nitsche of the Lamont-Doherty Earth Observatory and Columbia University Climate School to the Coastal Call. Dr. Nitsche is a leading marine geophysicist whose research in sediment processes and morphology of coastal areas, including Long Island Sound, has made him a sought-after expert. From the depths of the Hudson River to the ice sheets of Antarctica, Dr. Nitsche employs advanced technology like high-resolution acoustic maps and 3D data visualization to reveal the secrets held in the seafloor. Through his work, Dr. Nitsche is unveiling the rich story of our planet, told through layers of rock and mud. From a local perspective, Dr. Nitsche's research is vital to understanding our own backyard. He has spent years mapping the submerged landscapes of the Hudson River estuary and the Long Island Sound, investigating how sediment dispersal and coastal erosion impact the health of these crucial waterways and their vulnerability to storm surges and sea level rise. But his scope expands to the poles, where he is a leading voice in polar research, traveling repeatedly to the hostile environment of Antarctica. By mapping the seafloor adjacent to massive ice streams, his team reconstructs the history of glacial retreat, providing critical data on how fast and how far the ice sheets have retreated in the past. We're fortunate to have Dr. Nitsche visiting Fairfield to deliver the Center for Climate, Coastal, and Marine Studies monthly seminar and sharing his work with us today. So let's dive in, literally and figuratively, into a conversation about the stories written in the mud and the power of technology to reveal these unseen worlds with today's guest, Dr. Frank Nitsche. Welcome to the Coastal Call, a podcast by the Fairfield University Center for Climate, Coastal, and Marine Studies. Today's podcast is generously funded by the Achilles and Bodman Foundation. I'm your host, Rob Nazarian, founding director of the center. Joining me today in the studio is Professor Tyler Griffin, assistant professor of biology at Fairfield, whose own research is in the area of marine invertebrates, such as mussels and oysters, in Long Island Sound. Welcome, Frank. We're so fortunate to have you with us today.
Thanks for having me. It's a pleasure.
In the introduction, we talked about your work as a marine geophysicist. Could you start by defining what it is that you do as a marine geophysicist and what tools are in your professional toolbox that you're using when you're looking at the seafloor?
Sure. So marine geophysics is basically geophysical methods applied to the marine environment. They're like remote techniques. So we're using a lot of sonar, sound techniques, all the way from like simple echo sounding to what's called seismic, like loud seismic instruments to basically image the oceans, the bottom of the oceans, and what's underneath the oceans. Technically, it also includes like gravity, magnetic measurements, heat flow measurements, basically all kinds of physical measurements of the ocean and the ocean sediments. But my own focus, I think I started off with deeper seismic, but then now I'm more concentrated on the shallower surface and subsurface environment of the ocean and of coastal seafloor areas.
I have a question then. What kind of depths are we talking about looking at the seafloor? And are we mostly talking about shallow areas, or do you do any work sort of off the continental shelf into the deep sea? And are there different tools that you can use? Are ones better calibrated for different sort of penetration through the water column?
Yeah, there are different tools for shallow and deep water. So most of the coastal work is all very shallow, like say like 100 meters and less. Work that I've done around Antarctica includes also, well, the continental shelf is deeper there, like 300 to 1,000 meters, but also been working in deep ocean areas, continental margin, continental rise areas, which are a couple thousand meters deep. The tools are in principle the same, but you use different instruments with different frequencies. If you work in deeper water, you need deeper, lower frequencies that have more energy to get all the way to the deep of the ocean. The trade-off is basically that you lose some resolution. If you work in high and shallow waters, you can use higher frequencies. You have a better resolution.
Great, thank you.
And so we've talked about your work in the Long Island Sound as well as your work in Antarctica. How does your work on local systems connect to larger global research that you're doing in Antarctica? Are there any similarities in either your findings or the tools that you're using to conduct this research? And how do you connect these two projects that are on such different spatial scales?
Some of them are different questions we are going after, but there are also some similarities, especially in the local areas. So like Hudson River, Long Island Sound, created through glacial processes. If we work in Antarctica, we're looking at footprints of past glaciation on the continental shelf, how they evolved, like how far the ice reached, how it retreated, how it moved forward, which direction the ice was flowing. So we do see now and then also like features like this in the local environment, and then in a more smaller things, there is definitely also habitat in the deep ocean, habitat mapping going on, even though I'm less personally involved in that, but there is some overlap in this direction too.
When we were getting ready in the studio today, you mentioned that you go out regularly to conduct fieldwork. And so I'm curious to know, what are some of the challenges that you face when you're out in the field conducting seafloor mapping? And is there a particularly interesting story from the field that you'd like to share with our listeners?
I mean, that varies again quite a bit. If you do expedition like in Antarctica, where you're out for 2 months on a ship, where you can't go back to shore in between, or if you work locally. So you work with much smaller ships here, and then has more to do with the scheduling of the boats. Also, if we work small boats, and we're more dependent on the weather, see if there's good weather. But also we have the advantage of, okay, if it's a bad weather day, we don't go out here. Whereas if you're down in Antarctica, you're there for 2 months and you have to take what you get. There's a lot more changing of the plans going on down there, basically. You have your plan A, you have your plan B and C, and even plan D.
Do you have a particularly interesting story for our listeners for your fieldwork? One story that comes to mind when you think about the joys of fieldwork, or perhaps some of the frustrations of fieldwork?
I mean, the joys of, cool. If you go down in Antarctica and do survey and a seafloor, sometimes a lot of it is really new. There have been areas where no one else has mapped before. It's basically you're filling in a blank piece of the chart of the world, which is cool, and it's just amazing environment. But it can also be very frustrating if you want to map and there's a lot of sea ice that prevents you to go there. Locally, the interesting stories is sometimes, like in the Hudson River, we saw a lot of indication of shipwrecks and other stuff, which is very interesting to see, which is not really part of the main project, but it's a very interesting side story.
That's very cool.
So when you're down in Antarctica and you're doing this field work, you mentioned sea ice might be a problem. Are you on an icebreaker ship that can sort of traverse that, or is it really sort of a hazard that you need to avoid?
No, we are actually using icebreakers, at least until now we have been doing it. The US has decommissioned the last research icebreaker for Antarctica, unfortunately, just this October. But because you can, there's different level of sea ice. Like with an icebreaker that we used, we could easily go through like thinner ice that like 0.5 meter or to 1 meter. But if there's portions when it gets thicker, when you either have to break ice, which takes a lot of time and fuel to do, or you have to go around it. And sometimes there are like, icebergs in the way, and then you cannot really break. So then,
right.
They're too thick.
And then as a biologist, I have to ask, do you see, when you're out there near the sea ice, do you see any wildlife that you encounter?
Yeah, so usually the ice edge, we see a lot of penguin and seals, because when the sea ice melts, we go in the summer when it's melting, then we use a lot of nutrients, and it's very productive. So that's where a lot of all kinds of penguins and seals like to hang out, because there's a lot of food there for them. And then occasionally we see also whales. Also, most of them seem to be surfacing when I'm like sleeping or not on bridge. But there's a lot of penguins and seals you do see there, which is very exciting, even for a non-biologist like me.
Are there biologists on your crew, or when you go out, is it mostly for geophysicists?
It varies. So on the big icebreaker, because there's a long expedition, there are usually different groups on there, more than one. On some of my expeditions, there were biologist teams on it. And others, there were like more geology, oceanographer, and geophysics. So it's usually there are multiple teams, but I've been on expedition when we had biologists, and it's interesting to see when they catch krill and do it and look at those, and you get more, they know more about the environment and biological, and you learn a little bit about that too, which is very cool.
Yeah, it sounds really collaborative. especially being in such close proximity to a lot of different science being done.
Yeah, you help out each other because there's a limited number of people for each group you can bring on a boat. The ship operates 24 hours, 7 days, so you're like 12-hour shifts. And then you do help each other when they need like a hand to the lower device or do some sampling and things like that.
This all sounds so interdisciplinary and very similar to how research is done through Fairfield Center for Climate, Coastal, and Marine Studies, in which students and faculty work in interdisciplinary teams to solve large-scale problems. And so it sounds like these opportunities in Antarctica are very much a microcosm of that, in which you're doing work as a part of an interdisciplinary team. Our listeners may have a follow-up question here that I'd like to ask. If you're looking at mapping the seafloor adjacent to ice sheets, how do you use this data, this analysis, to relate it to future climate change? And what's the importance of conducting these sorts of studies?
Yeah, so when we go out mapping, so usually it sounds like on seafloor mapping, so we find features on the floor that indicates like, we call them ground wedges, but it's similar to moraine here, where basically indicates a still stand of the ice. We can tell like the ice moves position and then it moves further. There's indications where we can see which direction the ice flows flowing at different times. And then we work with geologists who take samples, and then they might be able to date those features. So we get basically a chronology, a timeline of how the ice was moving ahead and also how it was retreating, basically the last warming after the last maximum glaciation, how it was retreating so far. So this can all be fed back in ice sheet models today. So we can trust these models better if they're able to really reconstruct how the ice was flowing in the past and how it was retreating in past warming episodes. And if then they can extrapolate into the future and see like, okay, how different processes might impact, and more warming might cause further retreating of the ice that we have today.
That's so exciting that your studies not only have implications for the past, but also the future. Many of us at Fairfield are looking at future changes in climate, but in your work, you get to go in both directions, which is particularly exciting.
Speaking of the practicality of your research and the applicability, you are a leader in data visualization. So why is the visual presentation of geological data, seeing the seafloor in 3 dimensions, why is that so crucial, not just for other scientists in the field, but for policymakers and the public to be able to see these sort of abstract, large-scale, geologic, ice-related features? So can you comment on that?
I mean, I do it for myself because if I visualize in the right way, I actually can interpret this feature. I can identify these features much better than if I just have like a map drawn with contours. There are a lot of little details you really only see if you do basically a nice 3D visualization of the features. And then again, as you said, once I understand what I'm seeing, I can demonstrate this much more easily to other people. It's much easier than, a good image. It's worth like 1,000 words. Basically, it's much easier to explain this to other people, stakeholders, politicians, other scientists, if they see certain features that's so obvious how it might be created rather than an abstract text where you just describe it.
I think that's especially important too, right? Because on land, we're familiar with geological features because we see them every day. We pass a hill or a mountain, but the bottom of the ocean feels very foreign to us, really far away. So I think from my perspective, you putting a visualization on saying it's a little different, the geological features, but there are still these sort of processes that happen on the ocean floor, and it gives us something to sort of connect to, especially from someone from not a science background.
Absolutely. And something that's been all over the news and at the forefront at Fairfield University over the past couple of years has been artificial intelligence and machine learning. How are these fields beginning to influence your area of marine geophysics? Are these tools being used to perhaps automatically identify features in the seafloor, or are they not yet being used in marine geophysics?
I think we're in the early stages. I mean, I haven't really used much of these tools myself so far, but I've seen others. I know of other studies that are trying to train this machine learning algorithm to identify those features, but also to process and clean up some of the data we're using. So it is happening. It is not quite in production ready, but it's quite very exciting to see where this might go. And I think there's a lot of potential, for things that take me maybe weeks to do manually to maybe have a algorithm doing in a day or so. So that will be definitely changing.
Absolutely. And as a part of that, your research generates massive amounts of data. We were talking about that before we went on air. And thinking about the opportunities for AI, machine learning, and other algorithms, what are the ways that you deal with big data for your research? And are there any opportunities for students that are interested in big data in the area of geophysics?
Yeah, so we do. I mean, with big data, we basically have big computers and a lot of disk space to do it. But we also, over the last years, I mean, the last decade really, a lot of the data now goes into public available repositories, so available for other people to access. And there's definitely an effort being doing to kind of standardize the format, how this data are archived so that it makes it easier for people to bring different data sets together. We're not there yet for all the data, especially with older data. They might be stored in different formats, but with new data, we're really trying to bring all the data together in a different format and makes them accessible. And there are other efforts going on where like data that might be stored in different repositories, so that might be like bringing in like interfaces that you can link to different repositories in the same time. But it's all evolving at the moment, I think. But this is definitely the direction it's going.
And sort of taking a step back, sort of a practical question, these data that you're collecting, they're acoustic data. Could you explain in simple terms, this is mostly for my benefit too, how do you use sound exactly to see layers within the mud or the rock at the bottom of the ocean?
Yeah, that's a good question. So in general, what we're using is like an echo sounder principle. So all the different tools, or most of the tools I work with the same principle that we generate a sound pulse with a transducer that's sent down to the ocean. So either it's get reflected on the seafloor, or if it's if it's loud enough, if it's enough energy, there will be some reflected at the seafloor, some will penetrate into the seafloor and get reflected at different layers underneath. In general, what we're doing, we time the signal when we submit it, and then we listen to the return that's been reflected from the seafloor. So we measure the time it takes for the sound to go down and come up, and we basically divide it by 2. So, going down and coming up. And then critical for that is also to know the speed of sound in the water column. So once we know the speed of sound, we basically can derive the distance from measuring the time. And that's the main simple principle that all the acoustic sonar techniques work on.
I think it's really interesting too, because in principle, it works exactly like how echolocation works in the animals that have evolved that kind of capability, like the bats and a lot of marine cetaceans too. And we've sort of co-opted that sort of ability that animals evolved naturally to better explore sometimes habitats that those animals live in. I think that's really cool.
Yeah, it's exactly the same principle. And then modern systems, they can basically, instead of just one echo sound signal, they can have a beam of, 400, technically it's one sound beam, but they have different receivers so they can determine from which direction the sound comes. And then we get technically like up to 400 beams at the same time. That's very impressive.
And are these sound pulses, the initial sound pulse, is that like a frequency that we could hear, or is it sort of beyond our sort of human ear ability to pick up?
It varies a little bit from where you work, but a lot of the deep water ones, they use Antarctica, they operate around like either 12 kilohertz, some of them like 3, so definitely in the audible, like you can hear them. If you go on the ship, you're like, you hear like the clicking noises. I mean, if you use seismic, they're even lower frequencies that you really hear a boom. I mean, it's only like some of the higher frequencies in shallow water that maybe they're like in the 40 or 100 kilohertz range. So that would not be audible to humans.
Interesting.
I'm going to take us back to Long Island Sound for a moment and the Hudson River. You mentioned you've done work there, and certainly Lamont-Doherty, where you work, lies right on the Hudson. You mentioned previously that you've made some discoveries there as a part of your seafloor mapping with respect to shipwrecks. Could you give us an idea of what sort of shipwrecks you've seen underwater, and have they previously been identified, or were they new discoveries? And then as a follow-up, have you understood or have you come to understand any of the history behind them?
Yeah, I think there's a lot of, for the Hudson River, who have been involved for many years, the early 2000s especially. Yeah, there was a lot of interesting stories what we've seen. And with the systems that we use for the mapping itself, we don't get necessarily a very detailed picture. We can identify larger objects, and we can. So I think we found over 150 objects, potential shipwrecks in the Hudson River that we mapped. And then there was another survey that NOAA did. I mean, some of the shipwrecks were known and them on the charts already, but NOAA went out and mapped those shipwrecks in greater detail. And that was done with also with Stony Brook University together. And some of them turn out to be old 19th century barges of coal. And there were like one or two were sent divers down to look more on the history. They came apparently from Pennsylvania. Others are more modern ships that sank like somewhere in the 20th centuries or something. Sometimes we don't necessarily see a real shipwreck, but there was features we saw near Peekskill in the Hudson River, and we couldn't really explain what it was until we go and give talks, and then someone pointed out that that might be where, like after World War II, all the Liberty ships were moored. So they were sitting there for a long time, for a decade, and then left an imprint on the Hudson River.
That's very cool.
Yeah, I mean, the coolest thing, I think, we think we might found where in the Revolutionary War, where the Americans did a barrier. I mean, there was a chain, and we were looking with NOAA for the chain. We didn't see any indication of the chain, but we saw where they had spear-like barriers built in the Hudson River. I mean, the wood and the spears are gone, but they're like a line of stone piles on the bottom of the river that we could identify, which was very interesting.
And that's incredibly impressive that to be looking underwater, you can see with that high of resolution to make these inferences about being related to the Revolutionary War ship or others. That's incredibly impressive.
Yeah, keeping it here with sort of our local environment, Long Island Sound, we hear a lot about sea level rise and coastal erosion as problems for coastal communities. I wonder if you have any comment for community members around here. How does your work in mapping the sediments and understanding the history of our coastline, how does that translate into preparedness for future planning for coastal community members?
That's a good question. So I'm sure if it's a direct link to that, but we do see a lot of features that from how the Long Island Sound was flooded in the past, how it is changed, where sediment have been accumulating when there was space made by rising sea level. So this might be some things that might be able to link to the areas of potential sea level rise in the future.
So understanding in the past when sea level rose and in the geologic past, we saw that sediment accumulated in these pockets and it transported this way. Perhaps something similar might be happening now that we're also seeing this sort of contemporary rise in sea level. Interesting.
Turning now to our students, Fairfield has a fantastic reputation and history of doing research with undergraduates. Undergraduates on campus, some as early as their first year, are involved in research activities in the groups of faculty on campus. And so just to think for a moment about an undergraduate that's interested in studying marine science or marine geology, what's one course or core skill that you would recommend they focus on?
That's, I don't know, it's hard to point it down to one specific course. I think there's a lot of basic, geology, geophysics, understanding that's very important. I myself teach GIS, digital map making and things, which I think is very critical skill for a lot of students to have. That helps.
So GIS is certainly a course. Are there any skills perhaps that they could gain through research? Maybe not particular content areas from a course, but any critical skills in research that would be helpful for students to be competitive in this field?
I think any kind of real research experience, I think it's good. I mean, it's one thing for a student to have all the theoretical knowledge, but having some practical experience, I think either in the lab or in the field is really valuable. I could imagine that people like, well, if I look at students that I might hire like as interns from other universities, if somebody has already like some experience in this area, it's like field, then know what they get into. If they have to work in a lab or in the field, that's a big plus, I would think. So that's really good if students here get involved in research early. I think that's a big plus for them.
And then when you look at the progression of geoscience in your field, what is the most exciting or emerging technology that you think a current Fairfield student might want to pay attention to and really learn about?
I've already mentioned AI, machine learning. I think in all fields, this is really common and important tool. Yeah, it's hard to predict if there's any like specific technique. I think they seem to be all like evolving. They're getting smaller, they get more sophisticated. You can go more into detail. I mean, for marine research in general, autonomous vehicles are good, either like for like drones at underwater mapping. You can get closer, you get more detailed pictures. You're not depending on a ship necessarily. And it's, probably the similar for land-based geoscience, like airborne drones and LiDAR techniques, providing such a high resolution to get a whole another level of details where you can see like processes on a larger scale, but in detail that you couldn't see before, that really reshaping. So a lot of new LiDAR data that I've seen on land, or like high resolution multibeam data that we collect, that reveals like features on land or on underwater that people haven't seen. They saw like the big hill, but now you see all the details, that maybe how the hill was formed or how it eroded over time. So that makes a big detail.
And so you just mentioned that autonomous vehicles are emerging technology for students to be aware of that are interested in this field. Let's talk for a moment about autonomous vehicles. How have they changed the study of the sea floor, particularly in your ability to get underneath the ice? Are there any areas of expansion you would expect in the next few years for autonomous vehicles? How are they changing our ability to map in previously hostile conditions?
I mean, the few studies that I was involved or that happened when I was on a ship. In the beginning, it was more like prototypes of system. Now they're more off-the-shelf system. That's definitely a change. But as you said, we now can send those vehicles under the ice shelf that are too thick for you cannot break. So they're like hundreds of meters of ice. Yeah. They were like inaccessible underneath. So we can actually map there, like how warm water actually gets to the ice, how much there is. We can look for features. And the other thing that also more my field is happening is when we map from the ocean surface from the boat, we have to use slightly stronger sonars, and the way physics works, we don't have the fine resolution of the detail of the features. We can see certain features, but we don't really see them. And then sending a robot drone underwater vehicle like down there and mapping much closer to the feature, we can see much more details on those, and then get a finer resolution of how the ice has changed over time. So that's really changing it. And those vehicles, they're becoming more common. They have more endurance. They can longer ranges. I mean, there is a company called Sail Drone that actually sends now mapping vehicles for many weeks, so even months out in the ocean mapping. They're remote controlled, not totally autonomous, but it's like amazing what they can do with these vehicles these days.
And so in many ways, these vehicles are complementary to the work that you're doing, where you're doing the initial measurements and these vehicles are going in to make more fine-scale measurements, for instance.
Yeah, at the moment, it takes a lot of time still, like for fine scale, for a vehicle to map certain areas, where from the ship we can map less resolution, but a larger area more easily. And you still need a ship for some of those vehicles to deploy those, to monitor those, and service those autonomous, but they're becoming more able to go for longer range missions for longer times. But
So I'm curious, in light of the excitement and the potential around autonomous vehicles or AI, in your opinion, do you think like the next generation of geophysicists not only needs to have a background in sort of the theory and the physics and the geology, but also experience in computer coding or mechanical engineering? Or is there still sort of a space to have a collaborative effort where one individual focuses on one or the other?
I mean, I think there would be still a collaborative effort, but I mean, even before like my generation, I mean, geophysics always had a lot to do with, because there's a lot of data we generate in geophysics, but all the measurements we're doing. So it's always coding. So coding is another very important skill, I think, for students to have. So it was even when I studied like 20, 30 years ago, but, able to be coding and work with different instruments, have some technical abilities is definitely a plus. I mean, now you get more off the shelf, but often they have to do little, for a specific problem, for a little study, there have to be small modifications made, things put on the system or repaired. So I think some technical skills are valuable. I mean, often we go in groups where we all have similar backgrounds, but one is a little better in coding, the other one a little better in, electronics and mechanical engineering, some better in planning. So it's often a team effort. But definitely, I think coding is another important thing for geophysics for sure.
So we've talked about the importance of the interdisciplinarity and how it's so important to have interdisciplinary teams when you're doing field work, and we mentioned at Fairfield. When you're thinking about conducting a project and bringing together a team, what elements are you looking for when you're bringing together experts in different subjects to go out and to answer a larger question, or to apply for a large grant to go out and answer a question and do field work? What strengths are you looking for in that group that you bring together?
I mean, it does depend a little bit on the question that we're looking for. If there's certain things that we need, okay, I can do the mapping of things, but if we need to date it or some other component, we need like maybe a geologist who's good in taking samples, or one who's good in dating samples and good in the lab. So it's like, it kind of depends on what kind of the questions of the projects. Of course, overall is like, okay, do you know that somebody is a good team player? You get along on a ship together plays a big role too if you go on one of those expeditions. But in general, it depends on the question, what kind of analysis you want to do, what is needed to do the question. Often these projects come together for people you worked with in the past. They go in a certain direction, saying, people who can do this and that, or maybe sometimes you meet over coffee or beer at a conference and you have an idea, and then, I could do that, but I need somebody who can do this. Oh, I know somebody who can do that. So, you bring this kind of, often evolves organically, I would say.
So a lot of our students here at Fairfield are considering graduate school or careers in research, not necessarily geophysics, but if you had to give these students a single piece of advice that would help them navigate the world of graduate school, scientific research, or fieldwork in the physical or life sciences, what would you say to them?
I would say be open to, I mean, you probably have an idea which way do you want to go, what your interest is. First of all, pick something that you're interested in, because if you go to grad school, that's a long commitment, and there are going to be good times and tough times. So really doing something that interests you is like prime motivation to get through all this, I would say. But also be open to maybe do little, switches. When I started my studies, I was not necessarily planning to go into this field, but at some point in the career, there was like a opportunity that opened that switched me in a little slightly different direction. Opportunities will come up, I think, but you have to be open to see those and maybe willing to take those if it's in the broader range of your interest, I think.
To take a wide view for our final question, what continues to drive your passion for research? And what gives you the most hope when you look at the future of our planet?
Even if it's Antarctica or Hudson or Long Island Sound, we do this mapping, we bring data together, and there's always something new. I like mapping things, discovering things. I'm more like an observational rather than a theoretical like scientist. Yes, always there's something new that this year to discover, and that's very exciting. It's great to work with other people too. I like that as well. I mean, for the planet, at the moment it might look not so great for like Earth and climate time, but I think that we only have this one planet, and I think people will eventually realize that. And there is definitely a lot of things that's going on, and we need to understand it better to be able to manage this and to mitigate whatever it's coming. But I do think I'm an optimistic person, so I do think that we will figure it out. I mean, there will be sea level rise, there will be warming, we have to deal with it, but we will be able to manage.
With that, our deepest gratitude to Dr. Frank Nitsche for being with us today to share his expertise in and expansive knowledge of marine geophysics. Today's conversation illustrates how advances in technology can help us to learn more about Earth's past to better plan for its future. We hope this discussion has encouraged you to look more closely at the world around you and to discover your own research passions. That's all for today's dive on the Coastal Call, but we'll surface again next month with another exciting conversation.